Started then. Please stop me if I am not audible or you find something that is you're not understanding. Please don't hesitate. So what I'll do today is I'll say we last time we discussed a few algorithms, right? We discussed the Q learning algorithm. We learned the value policy iteration algorithm, and we learned the value iteration algorithm in details. So I'll first start off with implementing these algorithms on a grid world setting, right? So first of all, for people who were not, just to give you a recall that the value function of a state is defined as, what is it defined as? Say at a time t, I equal to 0 to say infinity gamma to the power I rt plus I plus 1, given st is equal to s. Right? This is how we define the value function. That is the expected reward, expected long-term reward, starting at a state. If you start at state S, so and what is the expected reward will you get? Is that what we had seen? And then we had found out two equations using the Q value function. One was Q of S comma A, again recall, was the expected reward again. Such that ST was A and the action at time t was A. ST was S and action at time t was A. And we use the relationship between the Q value and the value function to find out the equation that V pi of S was equal to summation of over all actions pi of A given S, all rewards and actions, probability of people who are not, I hope you all recall. If you do not, we can discuss, but you should look at the proof once again. So we saw that the value function could be written in terms of the probability distributions in this form. So now we said that this will converge if I just initialize this V of n to some value and I update the equation by this equation. I keep updating V. So V, say you initialize to all zeros, V0, and then you use this equation to update to get V1, then to V2 and so on. And then at V infinity, we said it was equal to the policy, the value function at the policy. So this was what the policy evaluation algorithm was. We'll see the proof of this next day. But then we said that now what are we trying to do? So now we said that we want the best action. So we had seen that the best action Q star or V star of whatever pi of star of S of a state is the maximum value of, in that state, Q of S comma A. And just putting the values into the equation, we had seen the improvement equation. So we had seen it was the argmax over the inner summation. So these two, and you see, you just check for every action, whichever action was giving you the maximum reward, you say that at a particular state, I will only choose that action. So whichever action is giving me maximum reward, I choose it. Fine. So this is what we had stated. This is how we found out the equation. And then we said that in the same way, we can improve the algorithm by using the previous value function. And this keeps on going hand in hand unless it converges to pi star and d star. So this was the algorithm that we came up with last day. And in the Q-learning algorithm, we had also seen that the same Q-learning algorithm could be also performed. So this is the Q value function. Whatever is the inner summation is actually the Q value. And we actually remember, right? So the the value function is nothing but the expected Q value, right? Over all actions. So that's why you take a summation over all the policies, actions over policies. So now we had shown that this update equation became this, so that it is slightly different. Here you actually are sampling a state and then observing what are the rewards. And then you keep continuing this algorithm. It's like the bandits algorithm. You see at a particular state what is the best action, and then you subtract the whatever was the best value function in the previous state. And this is how you keep on doing in the Q-learning algorithm. So any questions so far? So I just replaced this equation by a iterated update, and we did it last time in the previous class. What I'll try to do is, using these equations, I will solve a problem, and then you'll sort of appreciate how these equations actually work. So the problem is something like this. So if you see the trajectory here, or the grid world over here, so it says that there are patches somewhere here. You start from here and you want to end over here, but there are patches around it which are dangerous. So if you say reach this, you get a -100 reward. That is like, these could be some, you are moving on a cliff. If you go into this, you may fall off the cliff. So you want your agent to move past this and reach the endpoint. Is this clear to everybody? So this is the dangerous grid world setting. This is my original problem. So I just made this grid world, but yeah. So it looks like something like this. The red ones here are the ones that you don't want to visit. So you can clearly see that I would like to go something like this. This is me and my smallest step. Something like this I want to generate to get to the end point fastest. Okay, so let us see how to go about this problem. Okay, I'll just let us see the code now. I have these equations written in my code. So please, I'll stop sharing for my notes currently for once. Okay. Let me know if you can see my screen. Can you see my screen?
Yes.
Okay. So now these are all model-based methods that I told you, because the transition probabilities of the transition matrices are already known to us. So what I'll try to do is I'll import some libraries, and then I'll have a coordinate to describe this grid world. And rest of it is just this code I'm not going into. This is just showing the grid world and giving you actions. Okay, so this is the grid world. You can go over this code. This is to generate the graphics. The grid world is something like this. So you start from this state, and these are all the -100 rewards. And this code has a function. Where is it? Step, which will actually, if you give the state an action, it will return the next state reward and whether the trajectory is done or not. Is it clear? So this is exactly like the previous day's code, which we did policy improvement on. And this is exactly the same. If you move right, up, down, if you move left, you see if you're going out of the grid world, then you stay in the same state, else you go to the left. Similarly, if you going up, you go up, else if you increase the x, and so on. So recall that your value function or the policy iteration algorithm says that, say if you initialize for a particular pi n, some value function v0 to v0, you can keep updating this equation vk plus 1 in this form. And once you get it converges, you can put an improvement step in which you update the vpi and keep improving your policy, keep continuing do that. So you're actually, in this case, seeing which action maximizes your q value function. This is the q value function actually, right? So Any questions? So first you select get the value function, keep iterating over the values of v, update this equation, keep on updating, and then you update the policies. So let us see how to do it. So this is the policy iteration agent that I defined. So now as I was telling you, I'll define v as a as initialize it as all zeros. So this is of this shape. All these are all states, as you can see. This is one state. These are all states in this grids. Each of them, ij would define a state. Yes or no? So currently, if you are in this particular state, it would be one. This 7 comma something 4 would be the state that you are in currently, right? So that would fully describe your state. I can't see you. So in case you have a question, please put it forward. And then I will have a policy pi, which says that, so it will be again states. So see again, this policy pi is a probabilistic distribution. So for every state, I will have if I can take an action or not. I define therefore a 3D matrix. So for every state, the first two define the state, and the third one for the action. So if the current state is possible, current action is possible, I will take that action. So okay. So these functions resets the probabilities, so on. Let us see. So the state update. So how will we do the state update? So let's go to the policy improvement, policy iteration algorithm first. So what does the policy iteration algorithm say? You copy the previous v, you reset the value of v, do a policy evaluation. This evaluation is done with the current policy fixed. Policy fixed, right? And then you do a policy improvement. This is done with, can anyone tell me what will you fix? This is done with fixed value function, right? So now you just keep doing, as I was saying, policy improvement and policy evaluation. So, and if it has already converged, all closes the convergence criteria as we had done last time, the value functions has converged, then you have done with policy iteration. Is it clear to everyone? Okay, so now how do I do policy iteration is the question. So policy evaluation is the question. So let's go to policy evaluation. So policy evaluation, say we want to iterate for say 1000 epochs, and then for every state here, you see if it is a terminal state, then you're actually done. Then you go back. Else, what you do, you keep the old value of v, and then what you do a state update. What is the state update? So remember the equation again. So this equation is reward plus the value function at a particular state. So you are in a particular state S, you take an action, and on taking an action, you get a reward R, and you go jump to a state S prime, right? So that's what we are actually doing over here. Just check where is that code? Just a moment. Yeah. So you do an update state. When you do this update state for the current environment and the environment states, so let's see what happens. So if it is a terminal state, you return the value 0 because it's a terminal state. You are not going to get any reward. Else, what you do is update value is here. So in this update value, you take a step. So the step is akin to the inner summation over here. So when you take that step, environment.step, it gives you the next step and the reward. So that's what I had shown in the previous code, that this step function takes in a state and an action, and if you go up, it will just send you. So say you are in this current state and you go up, it will return this state, and the reward, which is -1. We have said that the reward is -1 at every point. Okay, so now once we get the once we get the state and action and the reward, so what we try to do is we update. So the Bellman equation here is deterministic, which means that this probability reward R, and this is just a del equal to 1, because there is for one state action, you just with probability 1, you move up. So you just get one value of R plus gamma sigma k, which we are just doing. So update value. plus the self dot probability. So this is the this one pi probability. Can anyone tell me what is this? You can clearly see the inner summation over here, right? Reward plus v of next state of x and next state of y. Is that clear to everybody? And what is this value? This pi of pi probability. Clearly look at this code. So we are summing over all the actions, right? Look at this and look at the equation here. So we have to sum over all the actions. So sum over all the actions A, right? So when you sum over all the actions, so I do a loop for that and I just update. So pi, this is the probability pi of, so if you're just confused, this is pi of action given the state. Is that clear to everyone? So this is the probability of taking that action given the current state. Okay, so now you take the reward and you see the value function at the next state. So that's your update value and you return the update value. Okay, so that's the value of vk plus 1. Just check that. So I will just keep on updating this value. Just check. So see, keep on state update, update state, and you keep doing it. And you see if it has converged, you break out of it, else you continue until maximum iterations. Okay, clear to everyone? Any questions? So what you're doing is every time updating vk to vk plus 1, vk plus 1 until convergence. Is it clear? Is it clear?
Yes.
Okay, so you just keep on updating that. And then what you do is, now it's a very next step is a simpler step. So next step, so what is it? Just recall is the policy improvement step. So you're trying to see, what you're trying to see is the maximum action that maximizes the reward, whichever action. So you'll see from this inner summation, whichever of the action gives you the maximum reward, you just select that action always, right? So that's what I'm going to do now. See, greedy action selection. So I'm going to always select the best action. What does this mean? So let's see, the current state is terminal. So if this current state is terminal, you return all the actions are equivalent, right? It doesn't matter. Else, you select which actions are good. So you take action dot in the environment, and then you see which, if the next value is close to the maximum value that you are actually getting from a current state, you just keep on adding that action, right? So if the next value is greater, so you make it, you clear it off and you append current CTR. So what you're actually trying to do is select all the actions that maximize the reward. But let's take an example and try to understand this. So say for the first action, so your maximum value was minus infinity, right? So you will always select that action, right? Because it is minus, everything is greater than minus infinity. So you will put that in the counter. So now you say every time for the next actions, if it is greater than the maximum value, I will just create a new list and I will append the counter and the max value will be changed. If they are close, next time, if they are close, I will just, so say 1 was selected. First, this, say action 1 was selected. 1 was selected. If 2 is also close, action 2 also gives. Action 2 also gives the same reward. Add that to list as well. Okay, that's what we keep on doing. And you return all those actions. Is this clear to everybody? I'll wait for a moment or two. If you have any doubts, please ask. So, okay, so I select the best actions and I put the probability of all those actions to be equal in this equation. So for all the actions possible, I'll just, if they are in the best action space, I make them 1 and then rationalize them by k, number of actions that are possible. So this is what I keep doing. And then let us see how it works. Okay, so it's running. See, so this is the action that I select. See, on this state, this is telling me go right, go up, right, go up, go left, go up, left, right. Are you able to see it? So all wherever there are 2 possible actions is like either of them are the same value. Yes or no? Clear to everyone? Is it getting the intuition? If you're not, I can't see you all. That's the problem. I'm not able to gauge with you. And value functions that I have over here is showing what are the values, which of the states at the optimality would have what value. So it says that around, so here it's around 20. So you will take 20 steps to reach the endpoint. Right? Is that clear to everybody? Any questions? We have solved a value iteration for a complicated MDP. I'm happy to share this. I'll have already shared the code. I'm happy to go over the code once again if you have any doubts. Any questions?
With respect to the output we are getting, means we
Yeah.
can have various paths, but
Yes. So this shows that all the paths. So you can either go up or you can go right. So that's what the code here is doing. I could take one action, but I did it a general code because why will I always select this path? I can always select this path as well. No, they're the same values. So it shows that you cannot go left here at 0. You cannot go down, but you can go up and right. Both are same value, right? Both of them are equally good. Right? Clear? Outreach?
yes.
Okay. That's why I was keeping on adding it to the list in case there are better actions, similar actions. Fine. So now the Q-learning tabular algorithm again, for a particular state and action, you take an action, sample an action. Oh, sorry. You do a step, go to the next state S prime, observe the reward, take the best action and subtract the current value. So this is what you keep on doing, right? So I'll run this code in the background for you to understand. But now let us see what it is actually doing. So say this is the Q-learning algorithm, right? So the Q-learning algorithm is quite different from the policy iteration algorithm because we are actually going on the in the surface actually, isn't it? So we are going around the environment and not just computing using the policy. So just check over here, the Q-learning sets. So this is, I am doing the Q-learning over 5 runs just because Q-learning sometimes is a bit noisy. But what I'm trying to do here is every time I reset the environment, that's not important, and I complete the trajectory, right? I keep on doing the Q learning. When will I stop? Can anyone tell me when will I stop this update? Any idea? For a particular iteration, I will stop this when I have reached this endpoint. Yes or no? So just check this thing. What I'm trying to do in this Q learning is I'm trying to complete the trajectory of the environment. So what is going to complete the trajectory? Say it is going to be an infinite loop such that the previous state you keep and the previous action you keep, and you will take a step as I was telling. So for every state and action, you will take a step. Say you take a step to S prime with an action A and you observe the reward. So that's what I'm going to do over here. The step here is again, just look at this. So the previous state is what I'm passing and I'm returning what I'm giving, what action also are you choosing? And I say I return the cumulative reward. And if it is a terminal state, I return the value of the terminal cumulative reward function. And That's what I'm doing. So actually I'm returning the total reward possible, and I'm returning the end state, whatever is going to happen. So if this is the terminal state, else what am I going to do? I will maximize that action, right? I will select the greedy action. That is, I will select this R plus S prime max over all actions, say A prime minus Q comma A. So let's look at this. So that the reward is what you observe. See, so again, you take a step, you get the reward, and you get the next state, which I have written as this state. So that is S prime is this state here. If you are confused, S prime is this state. Okay. So S prime is this state. What I do here is, for this state, look at this again, maximizing action. So I am choosing the maximum action and I am putting the value here. Just look at this. I'm just putting that value, maximum action. That's exactly writing this equation. And then I am putting the previous state. What was the previous action? Is this clear to everybody? And therefore I can update this equation, right? So I have got this delta t and I can just update using, for the current state an action, I will update the Q value of the previous state action plus the learning rate scheduler, which is number of times you visit that state and action, into the delta t. Is that clear to everybody? Look at this. So you have a learning rate scheduler which tells you how many times. So alpha n plus 1 is number of times you visit that state. We have defined this in the bandits, 1 by n plus 1. So that's what I'm trying to save over here. Number of times I am going to a state. So self.previous state and previous action will tell me number of times I visited that state, and I will multiply that with delta t. And I will keep on doing this Monte Carlo exponential updating. And then I will return. So self.end, this function returns the value if it is going to end or not. So if it is not going to end, I return false, that is not at the end, and I return the cumulative reward. And this I keep on doing. Is it clear to everybody? So argmax again are all those values which to break ties randomly. I'm going to select one of the values which is the best, and I'll just return that. Is it clear? Any questions? So the main crux of the code is this finding the state. So you will take a step based on the previous action, right? So whatever the action was, and you will get, given the previous state, you will get the next state, right? And you will get the reward. And based on the reward, you will select the maximizing actions and subtract the previous state and action value, Q value function. Is it clear to everyone? Look at this, it converges in 10,000 epoch, it gets to nearly this function. Again, it learns this trajectory similar way. It goes up and goes down. It learns a different function, but that's because we are just going around the environment. That's not a problem. If you can go and learn multiple iterations, nothing will going to change. But the most important thing here is the number of times the states were visited. Look at this. So these states were visited much often, which is what you want, right? You don't want the dangerous states to be visited because you don't want your agent to die. So these states, you see clearly Q-learning algorithm knows that these states are not supposed to be visited. Is that clear to everyone?
Yes. Yes.
It just is able to find out that because it's going. So why is it able to find out? It's because of this equation, because you are this self.q, you are maximizing the action value. Whenever you're going to that state, you have known that, oh my God, such a negative value I'm going to get. So this maximizing action will never be selected. So that's the idea. So your homework would be trying value iteration. So after the next two classes, I will give you a 50% of the assignment. And that would be much of implementation and some of coding. So some of these would be, so that would be 50%. At the end of the course, we'll get another 50%. That's the plan. So you try out and try to do the same using value iteration that we have already done in class and see if you get similar numbers. So any question do you want to ask? I'm happy to explain my code once again. It's a bit involved code, right? That's why it took like 30 minutes to just go through it. So the takeaway point is, for policy iteration, keep on updating the values unless you have updated the value for the current policy, you have converged, and then you select the next best policy, and you keep doing this iteration. And this works. For Q learning algorithm, you see, you start from a state and action, you take an action, and you go to the next state S prime, observe the reward. In the next state S prime, you select the best action, and then you select this delta T and keep updating this policy under convergence, until convergence. That's all there is to these algorithms. Okay, and these are all tabular versions and also the model-based versions. As we go ahead in the course, this probability matrix would not be available to us. And then we will have to employ other models, other methods to actually train this model. Because in the real world, you don't have the model of the world. You don't have, say, if I'm going to take an action A in current state, will I really get that reward? I don't know the probability of how much it's going to happen. You will have to learn these probabilities as well, but that's the next step. But today and tomorrow, next day, we'll just complete the model-based methods totally. That will build the foundations totally for the next set of algorithms, which will be model-free when you really have to gauge with the environment. Fine. I'll just stop sharing from my computer and I'll get back to the theory back again. So any practical questions? Okay. So now let's do a little bit more of theory. So what theory I'll do is, it's a okay, my screen is just showing. Why is it not rotating? Oh, give me a moment. I'll just leave and join from my tab. Okay. Okay. I think you can be able to see it now. Oh my God, why is this not working? Okay, now it's finally working. Okay, let's get back to it then. Yeah. So now we'll do a special class of algorithm called dynamic programming. So dynamic programming is one of the first RL algorithms people discussed. So it's in flavor of what you do normally in dynamic programming, that is recursion, right? And you try to make the recursion faster and faster. And that's what we'll be doing over here. Okay. So before that, again, to keep you all on the same page, I'm using concepts from this book of D. Barsekas, but I have changed it to have the same notation. He uses minimization. We are still going to do maximizations and so on. So you can look at the book of Optimality and Control and Dynamic Programming, Chapter 1, Volume 1. This is an important code to our algorithm to understand, because this will sort of give you an idea of, if things are simpler, what you can do. So for example, say v pi of s is the value function, right? Again, people, do you recall that it was the value function is nothing but the total reward you will get till the end, right? So say you are in state S, you take an action A and you get a reward st plus rt plus 1. You go to st plus 1, and so on. You get RT plus 1 until you terminate. You are going to add up all. This is the value function, addition of all rewards. Yes or no? You see that if you start from a state, if you are able to add up all the rewards, that's all you are seeing. Any questions? This is just a revision. Anyway, fine. So what you now I'll show you is we'll deal with two type of problems. First, today one, that is when n is fixed. Next day we'll be dealing with another class of problem when n is fixed, n is finite, but it is stochastic. So today we'll do a simpler version, which is called the finite horizon MDP problem. So it's called finite horizon because something like this. So you are in S0, you take an action, you go to S1, you take an action, A2, and you keep going unless you reach Sn. And this n is deterministic, is fixed. So for example, number of games in a series or in a world championship of chess. So you know that you'll have to play 15 games in a world championship or whatever it is. So it's always, and you know that in a series I'll have to play 5 games. So it's fixed number of steps. But in between the actions and the rewards and the states will be stochastic, right? Is it clear to everyone? And if the number of step itself is stochastic, we call it a stochastic shortest path problem or an episodic task. And infinite horizon problem we'll be seeing later. Is this clear? Where the number of steps is infinity. We have already discussed a number of steps to be infinity, and then we have to do discounting and so on. But for the first two cases, you need not use discounting because the summation as we had shown will converge because there are. Can anyone tell me why will? Can anyone tell me why v pi will be finite if n is finite? Any idea? If you have, this is the very basic question just to see if you people are following. If n is finite, why will v pi be finite? So v pi again is the summation of rewards, no? RT plus 1, RT plus 2, and so on. So if there are a finite number of steps, sum of finite terms is finite, no? Correct? Summation of finite number of finite terms. Okay. Good. So now let us describe this setting in particular. That is the finite horizon setting. So you start from say S0. You go to S1 by taking an action A0. Then you go to take an action A1. I go to S2 and so on unless you reach the terminal state. This is your terminal state. Throughout today's presentation, we will assume an MDP where the model is this. It is just to simplify stuff. Is over, so just over the next step. So this is called a controlled MDP. I'll tell you why. Or Markov chain, controlled Markov chain. Fine. So what I'm trying to say is this, that the rewards are deterministic for a state and action if the next state is known. Okay, so basically what I'm trying to do is recall in our first class, do you remember this value function? So look at this box that I'm plotting, or I'll just draw it over here. So say SK, you take an action AK and you go to SK plus 1. Fine. So the reward that I will get here, SK, AK, SK plus 1. Do you agree these three numbers will totally determine the reward I'll get? Fine, if there is no randomness. Do you agree?
Yes.
Okay. Because I am at a state S, I took an action and I got to state S plus one, as normally in an environment we keep doing. So remember that in our previous classes, we have already defined this function as the expected reward R as Sk, or Sk is equal to Sk is given, Ak is equal to Ak, and Sk plus 1 is equal to small sk plus 1. Isn't it? It was what did we define this as? We defined this as the three-step, three-argument reward function. Yes or no? We defined this as a three-argument reward function. So basically what I'm trying to say to you is, if I write down this equation, summation of I equal to 0 to n rt plus I plus 1 3 pi of is 0, so I will not even write t. I will write I plus 1 given, because I'm already starting at 0 at t equal to 0 is 0 is equal to 0. Do you agree that this can be written as a summation of r si ai si plus 1 summation of 0 to n minus 1? This is of course till the last state, because there has to be n states, not n plus 1 states. Is it clear? Is this the same thing? Basically, even if this, we are just replacing this three argument function over here. Fine. Even if there was stochasticity, we are accounting for it by taking the expectation. Is it clear to everybody? So now these are real numbers. So where r I plus 1 is defined as si ai si plus 1. So where time at state at time I, this is the action at time I next state, and this is the expected reward you get. So even if R was not deterministic, by iterated expectation, you can always write this as a summation of R st at st plus 1. Yes or no? Yes, you can do. And iterated expectations always will give you the total value. Fine. So that's the equal to sign I have written. So, but for now, you can assume that this is a real number. Is this fine to everyone?
Yes.
Okay. So now I say that, so I got this equation, and I say that at the final state, when I reach the final state, I have a reward for reaching a state. So this is an addition that people do in finite horizon problem, because say at the end of 14 matches, if a player wins the tournament, he's going to get a lot of cash prize or some trophy, right? So therefore, the winning, if the state is winning, you should get more prize, yes or no? So to account for that, we say that we add a reward function. So we make this, so v pi of s is defined as whatever is 0 you want to define, is defined as the reward at state n, reward at terminal state, reward at terminal state, plus reward at terminal state, plus summation of I equal to 0 to n minus 1. I'll draw the diagram. If you have any doubts, please ask. So it's like, again, S0, A0, S0, A0, S1, S1, A1, R of S1, A1, S2, and so on. And you till reach Sn, you get a reward Rn. Is it clear to everyone? So this is what keeps on happening. And this is the finite horizon MDP. Okay. So now this finite horizon MDP is defined on a, it's defined using a controlled Markov chain. And you have done this already. Since this is an MDP, it has to be a Markov chain because it's already there in the question. So it says that Sn plus 1 equal to, say, state J is equal to, say, just Markov chain. Can anyone recall what is the just a Markov chain? It's a random process where the next state depends only on
Just previous state or present state.
Yeah. The next state depends on the present state. So just Sn equal to I. So this is the Markov chain. A controlled Markov chain, on the other hand, says that my transition to Sn plus 1, my transition to Sn plus 1 equal to J also depends on the action at state A, or state Sn. So it's defined something like this. The probability of Sn plus 1, I'm just using shorthand notation, not putting i's and j's over here. An Sn minus 1, An minus 1, dot, 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 is same as, can anyone tell me what will it be? Very interesting. Same idea. It's independent.
Probability of Sn plus 1 given Sn and An.
And rest of it is independent. Given current state and action, past is independent. Okay. Fine. So now,
The one thing to ask, when the place you have written that R of Sn. Yes.
It's R of Sn. Yeah.
Yes. Means here the action taken in the last step to reach Sn, that is not being considered.
That is also there. Sn minus 1, An minus 1, and Sn. No. Once you reach the last state, you will get an additional action reward. This is there, no?
Additional one is Rsn.
Yes, that is on reaching an end state, you get an additional reward. Good question. Okay. Okay, let's play our old game then. So what's the old game that we'll be playing? Okay, I'll show you. First of all, let's define the value function, right? So v pi we have already defined is 0. This is just to recall your Bellman equations. 1 to n minus 1, reward of Si pi I. I'll tell you why I wrote pi I. Currently, you can write ai as well. Si plus 1 is 0 is equal to a. Now, can anyone tell me what is this expectation over? Is the first question that I have to ask you. Right? What is the expectation over? That is, what are the random variables here? Do you agree that given a policy pi, S0, S1, S2, dot, 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 or S0 is given, Sn, these are the random variables, yes or no? Fine. Because
yes,
you can clearly see that I am going to, where did I draw the diagram? Here it is. Markov chain, S0 to S1, S2, S3, and so on. Because why do I say that these are the random variables? Because I make the policy also here very, very simple. So I make the policy pi as a list of policies. Pi 1. So this is why it does not depend on actions. Doesn't depend on actions directly. doesn't depend on actions directly. So say I define a list of actions, list of policies. So pi 2 dot 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 pi n minus 1. At every step, I give myself freedom. At every step, I have the freedom to choose a policy, choose a deterministic policy. And what is this deterministic policy? So pi I is a map. Can you tell me what is this policy going to be? Tell me. Just a map from state to action. So AI is just going to be pi I of Si. Yes or no? Fine. What is the problem? Let's ask the question. Ask. I'm waiting. So I say that I define a list of functions. This is a set of functions. Functions that map from the state space to the action space. Right? So see, you see AI can be written as the pi of Si. Right? So what is the objective? The objective is to find that pi or the set of functions such that, tell me. So say this is all the policies, all possible policies. Tell me what will it be that maximizes V pi of S for all S. Yes or no? This is what we have been trying to do. So we are trying to maximize the value function of every state. That's it. Any questions? Okay. So I'll go ahead then. So now V pi of S0, again, I'm going to write it down as P pi, whatever expected value, R of, so, okay, I'll come to that in a while. We can do it, but the idea is something like this, that R of S0, A0 or pi of S0 and S1 plus R of Sn plus summation of pi equal to 1 to n minus 1 R of Si, Ai, Si plus 1 given S0 is equal to S0. Fine with everybody? So now tell me, what trick will I use to convert it into an equation that I already know? We have done this trick infinitesimal number of times. Very simple trick. Tell me. Do you see a recursion over here? Can I take an expectation of this conditioned on Si plus 1 or S1 in this case to be some S prime? Yes or no? By iterated expectation, I can keep conditioning, right? Things that I don't know. Because when I go back to the outer expectation, we have already seen P given Q, the expected value of P given Q is just the expected value of P. Because first you get a random variable in terms of Q, and then you take an expectation over that as well. So you get a real number. Yes or no? If you don't ask, I can't. Okay, so this can be written as expected value of R of S0 pi 0 S 0 S1 plus V pi of S1. Yes or no? This is again a recursion. This is just V pi of S1. And you keep doing this. right? So now you can see there is a pattern to this. Again, b pi of S1 would be dependent on what? S1 pi of plus b pi of S2. Yes or no?
Yes.
So there is, you can see a recursive pattern. So this is why the dynamic program will come in. So let us try to understand what is the dynamic program going to talk about. Okay. So we have understood this value function. We have understood how it is defined. We have understood our policy. That is, we are trying to find out the policy. Where is it? That maximizes the reward. I think I wrote it down somewhere. Did I not? Ah, here you go. This is argmax. Sorry. Whatever policy was going to maximize your reward, you're going to select. Your goal is to select that policy. Okay. So now I'm telling you. So since I already know, the idea is the intuition must come first in this case, because see one thing, since I already know the reward at a state Sn, yes or no? I know the reward at state n. I can just put down that value, yes or no? Correct? And then I can just go backtrack one step, that is Sn minus 1, and select the best action which will get me the maximum reward, yes or no? Because remember, I have seen V of Sn will be nothing but, or Sn minus 1 will be nothing but reward at Sn minus 1, An minus 1, Sn plus R of Sn. Yes or no? I already know this. So I will select only that action, An minus 1, that will maximize my Sn minus 1. Might get me the maximum reward. And I keep doing this backwards. This is the intuition. We'll show it even more theoretically and easily. But is the overall goal clear? And once I know Sn minus 1 values function, I can go back to Sn minus 2. And I keep going back to S0. So this is just a recursion. Instead of doing the recursion, I am doing a dynamic programming when I'm starting from the end and I'm going back. This is clear. Okay. Either you are understanding everything or understanding nothing. So, okay. So for recursion, what do we have to first define? Or for dynamic programming, what do you have to first define? The intuition, again, I've written, once we know the value of function of the next step, we can construct the value function of the current step. Tell me. First is we have to define a subproblem. For all the computer science students, you may know this, and people outside computer science. So this is a subproblem is, say for the, you have a problem P, you try to divide it into, say, problems P1, P2, Pn, so that each of these are easier to solve. And then you aggregate and solve the bigger problem, right? So first of all, we'll define the subproblem. The subproblem is defined this way. Say we defined a truncated policy pi I. Truncated policy of pi, which was equal to pi 1, pi 2. Let me write it down nicely. Pi 0, pi 1, dot, 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 pi n minus 1. So can you tell me what would be the truncated policy at step I? At step I, whatever steps is remaining, those policies. So truncated policy at state I are the remaining steps or policies. So say you are in state Si, you want to select it based on S of I, pi I, Si plus 1, you want to select pi I plus 1, Si plus 1, and so on. Yes or no? And you don't worry about anything of the past. So you are dividing this problem into a subproblem like this, that I am solving only the problem only after stage I. Is it clear?
Yes.
Okay. So now, so the truncated policy will be what? Pi I plus 1, pi I plus 2, and so on. Yes or no? Till pi n minus 1. Okay. So now what my claim
Yes.
is, the V pi of the ith truncated policy for a state S. Can you tell me what will this be? Can you tell me? First of all, one thing will remain, that is state at Sn. And then there will be the summation. All the rest of the rewards, yes or no? Reward of Si, pi I of Si plus 1, and so on. Yes or no?
Yes.
So k equal to say I to n minus 1, reward at Sk pi k of Sk and Sk plus 1. So this is defined as the truncated policy. So the definition is fine. So this is that's the reward, the remaining remaining rewards from stage I. If at state Si is equal to S. Fine. So now the first two questions define the subproblem, hence define the corresponding truncated policy is done. So now I have a few. So there are 3 questions and that will take around 30, 35, 40 minutes. So what are the questions? The question says that what is the truncated optimal policy? Say, so the first, it is given to you that pi star is an optimal policy. So tell me, what will pi star look like? So pi star, what is pi star? It will be like pi 1 star, pi 0 star, pi 1 star, pi 2 star, so on. At every step, it must be optimal. All the steps, it is optimal. Fine. So I understand that as well. So now I tell you to define a truncated optimal policy. Truncated optimal policy pi star of I. Can you tell me what will it be at stage I?
It will be pi I star, comma pi I plus 1 star till pi n minus
Good.
1 star.
Correct. Very good. So these are all these remaining policies. What I am going to prove to you is the principle of optimality first. First, I'll prove the principle of optimality. And I will ask for like maybe for some feedback from you how to do that. So let's try to see. The principle of optimality says that if pi star is optimal for the DP, pi star I is optimal for the ith subproblem. Now, very, very big statement. Looks very trivial, but not trivial at all. So it says that if pi 1 star, pi 1 star, pi I minus 1 star, and pi star I, which is a set, if this is an optimal policy, this is also optimal for the problem. So now, if I have to ask you how to do that, do you have an idea or a suggestion to how to start? How to prove it? Any method of proving that you want to use? Okay.
Induction.
So induction may work, but there is an easier method actually. This will be like 2-3 lines. By contradiction, let us see. Induction will also work. Yes, you can consider I star and then you go and go back. Induction is right. Correct. By contradiction is also possible. I think contradiction also will be similar to induction. Let us see. Okay. Say, so whenever we are trying to contradict a statement, what do we have to assume? Say, there exists a policy pi tilde of I, right? Such that V pi tilde is greater than V pi star I, right? This is what we have to assume, that there exists a better policy. And we want to show that it is not going to be true by showing contradictory, it is a contradictory statement to our beliefs. That's how we prove it. No problem. Okay.
Yes.
So now let us define V. Let us say for a state S, what is V pi star of S? Can you tell me how? What will it be? This is again the same equation. R of Sn summation of I equal to 0 to n minus 1 R of Si pi I of Si plus 1 given S0 is equal to S. So now from this, I would like you to think about how to bring in pi tilde. I have to bring in pi tilde somehow. How do I bring it? Sn plus, do you agree I can write this as 0 to I minus 1 R of Si pi I of Si plus 1. So it's a lot of i's here. Please pardon me. Let me write it as k plus 1. And then you have a summation of k equal to I to n minus 1. And reward of sk pi of, again, same thing. I'm just going to write down and then I will ask for a trick. So again, to recall, so I just wrote down it into two sums. Okay, why did I write it down into two sums? Say pi tilde I is equal to pi tilde I plus 1, and so on, pi tilde n minus 1. So do you agree that since the value functions are higher, what does it actually mean? If the value function is higher, the reward at Si pi I tilde I Si plus 1 will be greater than R of Si pi of Si plus 1 or Si and Si plus 1. Yes or no? This is going to be greater because value is the amount of reward that you are receiving, right? So if you're receiving more reward, then the reward will be greater. So it's like you can just construct it. Say A star at I, at stage I, is some actions A1, A2 for every state. So now I change this action space to A tilde I such that everything remains the same. A1, A2 dot dot, and I change say AK to something else such that the value function increases. So do you agree that the reward would increase for that state? Changed to increase reward. Okay.
So the one thing, like
Yeah.
for pi tilde, for one step, this may, if this is true for all the i's after from I to n minus 1, then okay. But it may be that from the total summation is greater for pi tilde than pi star, but for few steps this is not true. Then also it can be.
No, but that is true. But this is, I am saying for every possible I. This is for all I. If it is true for all I, then that cannot be true, no? The pi I can be between n minus 1, n minus 2, dot 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 till 1. So if it is validated at every step, then that is not going to work. That n minus 1, you have only one reward. So that is an optimal there. So for every step of I, if it has to be true, it must be true for the entire sum as well.
Yes. Means pi tilde will be then greater than pi star.
Yes, that's what I'm saying. Pi tilde is better. I'm already saying pi tilde is better than pi star. So, but it is the caveat is pi tilde is only for a truncated policy. Pi tilde is only for a truncated policy. You have to show that this new pi that you will be generating will be better. So I can write this greater than or equal to summation of k equal to I to n minus 1 r sk pi tilde of sk plus 1 s0 is equal to s. Right? So which means that this is greater than v pi of pi 1, pi 2 star, dot 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 pi I minus 1 star, and pi tilde star, or pi tilde I. Right? So clearly there is a contradiction, but v pi star is the maximum by definition. Therefore pi tilde has to be equal to pi star. Clear to everybody?
Yes.
Okay, so this is the principle of optimality. So now I will define an algorithm, how to solve it. So I have a proposition for you that will be proving, and the algorithm will be hence proposition. It says that the finite horizon problem can be solved for the starting state S0. Okay, you can solve it for the starting state S0 by the following such that, say, v pi star of S0 is equal to something that we define as V0 of S0. So we will see why is it called V0 of A0, but is this clear? So this is a set of functions that we are going to define. So for the initial state, I will say that, say the best policy I already can know by the following recursion. What is the recursion? It says that Jn, this is the base case, Jn of Sn, can you, or sorry, Jn I'm writing, Vn of Sn. Can you tell me what will this be equal to? The last step, Sn, the value
R
function
of
of the,
Sn.
very good, R of Sn. Because at the value of the last state, value at terminal state is the reward Sn, last step reward, last reward, or terminal reward. Good. And now I say for all k in n minus 1, n minus 2, dot 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 to all the way to 0, vn minus 1 or vk of sum sk is the expected value of, can you tell me what will it be? So you are in a particular state, sk will prove it, but the intuition has to be there. Is the idea. Sk plus 1, ak, right? Is the max of all the actions in ak such that the expected value, tell me, it's again a truncated value. We have defined this. R of sk, ak, sk plus 1 plus the value function of k plus 1 at sk plus 1, given that sk is equal to small sk. Is this clear to everybody? So because my entire future has been collapsed. Future will be collapsed in sk plus 1. Yes or no? Because all the future values, again, remember, why am I saying this? I will prove it, but the intuition is, again, this, right? We have seen this. Where is it? Yeah, that I could write the value of the 0th variable and I could put the rest of it to the next state. Yes or no? And the next state also, I could write it the reward function and put it to the next state. And that's what I'm saying. Recursion will be backwards. I will keep going backwards and selecting the best action. Fine. I think the proof will make more sense of it, but let's see. Okay. So now we have to say that if that is true, so we define this is ak is equal to pi k of sk, right? Then pi 1 star, pi 2 star, dot dot dot, pi 0 star, pi 1 star, pi n minus 1 star is the optimal policy pi star. Is the problem statement clear? Is what we have to prove, that you start from n and you keep going backwards, and in each step you select the best action ak, select based on the reward r of sk, ak, sk plus 1 and the value of sk plus 1. Right? I'll take a pause for a moment before I go into the proof. Right? So this could be your, you could try and do some homework where you are trying to do the dynamic programming, but yeah, we'll go to a concrete example, then you can write that. Yeah. So now, how do we prove this is the question. Now the base case is simple to prove. Base case, no action to select from. Yes or no? Do I have an action to select from at the base case? So therefore, my v of Sn is just going to be the reward of the value of the state function at Sn. Yes or no? Fine.
Yes.
So now what do I do? So I'm trying to now do as Otrich told me before, can I do an induction? Can I do an induction? This is the proof you were referring to, and I'll do it for this proposition. That is, say pi star of k or k plus 1 is optimal for v pi star k plus 1 subproblem. This is why we prove that all the subproblems are optimal in themselves. So if we say that v pi k plus 1 is optimal for all k plus 1 for the policy value function in this subproblem, what can I write? V k to be. Can anyone tell me? Or the v pi k, pi star k. So we want to find v pi star k. How do I find this? So again, do you agree that is the max of pi k plus 1 pi n minus 1 v pi of, or the expected value of, reward at Sn plus summation of I equal to k to n minus 1 reward at Si pi I of Si plus 1 given S k is equal to S. Is this clear? Is this correct? Is this fine? This is what the subproblem is. You start from Sk, you select the reward, go to Sk plus 1 on pi k, and you keep going. Yes or no? Right? So again, if it is clear to you,
Dada, that maximize means
yeah,
for each pi means pi k plus 1 for each we are maximizing.
that's exactly what the problem is, right? So you want to find pi k plus pi k star. What is pi k star? That is pi k star, pi k plus 1 star, pi k plus 2 star, and so on.
Acha, 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 got it.
So this means that all the steps or policies are optimal. Then only you can get the maximum reward. Yes or no? We proved that just now. All the steps have to be optimal. Fine. This is
Yes.
how you define the subproblem. Okay. So now once I define the subproblem, can you tell me, can give me a hint how to do this? There's a reason I put a bracket on this, but some hint. Can I write this as, I have already done this once, Sk pi k of Sk plus 1 plus R of Sn plus I equal to k plus 1 to n minus 1 R of Si pi I of Si plus 1 given Sk is equal to S. This is the same thing, right? I just put the first term out. Now, can you tell me what would be the second term? This term. What can I do to this?
That would be v pi star k plus 1 is if we use linearity, and
We can just use iterated expectation again.
oh yes, sk plus 1 then.
Is equal to say some S prime. Okay. So this is again, I'm going to put an expectation here because I don't know. Whenever I don't know, I always condition more. That's the idea. If there is an expectation outside, I can always put more conditional expectations inside. There's not going to be any problem. That we have proved also in the past. So now this becomes equal to R of Sk pi k of Sk plus 1 plus, as you were saying, V Sk plus 1 Sk plus 1. Did I write things correctly? In the proposition. Yeah, I wrote Sk plus 1. So V Sk plus 1. This is pi of the policy Sk plus 1. This is the sub policy, right? So, and conditioned on Sk equal to S. So now this is maxed over pi k and also max over pi k plus 1 pi n minus 1. So now, can you tell me one more trick to do? See, this inner summation, if you have to maximize, right? Which term depends on pi k plus 1 to pi n minus 1? Which term just depends on that? Only this depends? Only term 2 depends on pi k plus 1 dot 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 pi n minus 1, yes or no?
Yes.
So I can just write max over pi k plus 1, pi k plus 2 dot 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 pi n minus 1, v pi k plus 1 is k plus 1 is k equal to s plus reward of sk pi k is k plus 1 expected value over expected value and maximize over pi k. Fine. Okay. So now what is this? So when you maximize, we have already defined this. We have told for the subproblem pi k plus 1, we already have the optimal. If we already have the optimal for the subproblem, I can just replace it by that, right? Yes or no? Yes or no? This is what we had started to prove, or started to prove initially.
Yes.
Good. So it says that you can keep on doing this back in time and you will still get the optimal policy. Okay. So since we have some time, I thought we would not have time, but if you have understood, we have, and if you have no doubts, I would try to do an example of this for this. Okay. So that we can complete dynamic programming today itself. I thought I'll have not got enough time. So it's in my next note. I'll copy it here and we'll do this now. Okay. So the question here is, say we are playing, as I was saying, a world championship of chess. With n games, the person will move with more wins the matchup. Formulate a strategy for the person to win. The scores tied after n games, it goes to sudden death. The actions that the players can choose are playing a conservative approach or playing a aggressive approach. If you play the conservative approach, you never lose or even never win, and you can assume P of draw to be greater than probability of win. But and if you play an aggressive approach, you never draw. That is either you win or lose, right? And if you play a conservative approach, you are going to either draw or not, or you are going to lose. These two are the strategies that you are going to have, right? So now the scores they are given to you, as you know in chess. For a win +1, for a loss -1, 0, sorry, and for a draw You have half a point to both players, right? So now first question that you are told to ask is that number one question, what should be your state space? Any idea? What could be your, how could you define the state space? Your objective is player versus opponent you are playing to make player win. Right? Your objective is to make him or her win. So what should be your state space? Do you agree that if I have a state space is defined as points of player minus points of opponent, I can compress the information into a single number. If S is greater than 0 after n games, player wins. S is less than 0 after n games, opponent wins. S is equal to 0 after n games, sudden death. Is this fine? Any questions? So basically, you start at 0. If player wins, you go to 1. Win, you go to 1. Lose, you come back. Lose, you go to -1. Just like a Markov chain. Win, you go back to 0. Win, lose. Fine? Clear?
Like one thing we are deciding what should the player do after end games. So the state is one state.
Oh, no, not after. So what is the state space? The state space is the difference of the scores. It can be 0, it can be -n. So if all the games player 1 loses, then your state would be -n. Else it would be -n -1, -n minus or -n plus 1, -n plus 2, and so on till n. Yes or no? So if player A wins all games, you will get n points. Yes or no? Your opponent will get 0 points. So S will be n. Correct?
No, I was actually asking about states. How many states are there?
So you can clearly see there are how many states? -n to +n, all the integers, and 0 also.
Acha, okay, all right.
So you have 2n plus 1 states. Right? It can be, the state is defined as the point of player A minus point of player the opponent. So there are 2n plus 1 states. You can be at -n and after n rounds, that you can be at +n after n rounds, or you can be somewhere in between. Right?
Yes.
Okay. So now I say that the state, if it is greater than 0, and after n games, you agree that the player A has won because points of player has greater than player points of opponent. Fine. If it is less, it means that the points of player is less than the player points of opponent and you have lost. If it is 0, you go to sudden death. Okay. So now first tell me what would be the reward function. The reward, say Sn or Sk pi of Sk plus 1. I am safely assuming to be 0 for non-terminal states. I am not putting anything. We'll see why it's not important. But I have a reward at the end, right? So S0, these S0 here are the stages of the match. And here, this is the actual Markov chain. Markov chain is defined over the state space. And this is the rolled out Markov chain. That is at S0, you can be at 0, and this is at 1, it can be minus at 0, then you can be -1 and so on. Fine. Okay, so I define the final reward as, tell me what should I define the final reward as? If S is greater than 0 or Sn is greater than 0, what should be my final reward? If I win the match, I get some positive reward, yes or no?
Yes.
So I can just say +1, right? If Sn is less than 0, I just say I don't give you any reward, right? And if Sn is equal to 0, what reward should you get? Can you tell me? This is trivial because at Sn, if you are tied, where does the match go to? Tied after n matches, it goes to sudden death, right? And in sudden death, it is no use playing the drawing strategy, clearly, because you are never going to win. So you will always play the winning strategy. So if you play the winning strategy, the probability of winning is PW, correct? PW percentage of times you will win, and 1 minus PW times you will lose. Tied after n rounds, you can at max win with probability PW. So it's like the reward is like the probability of winning here in this case. So if it is 1, it means you have won. PW is like the probability of winning if you are at tied, and 0 is you are never going to win. Is it clear? Right? I'm waiting for questions.
Yes.
So if that is fine, tell me what would VK of SK be? Max over.
The one thing to ask, if the player plays for draw in the sudden death, then means the game will roll on.
So if you play for draw, say you get probability PD as draw. Okay.
Yes.
So you say you got a draw. So you get that with probability PD. So again, it will go to so number of as long as you keep playing draw, you will at most get a draw. Say at the end you play a probability of win and you win. So this is the probability that you're going to win if you play n-1 draws after that. N-1 draws and a win. So it's already less than PW, right? Because you're multiplying numbers less than 1.
Oh, yes, 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 yes.
So it's no use playing a draw strategy. That's what I was trying to say. So it's always you have to play a winning strategy. Okay. So now I have to select. So now tell me first, what is the equation? Pi k expected value of reward at sk, pi k of sk plus 1 plus v pi of sk plus 1 given sk is equal to small sk. So now I tell you, I have to select the best action. So what are the possible actions? What are the two actions I have? Can you tell me? Pi k, two actions are play conservative and play aggressive. Yes or no? These are the two actions I have, right? At every step. If I play conservative, what are the outcomes possible? What can sk plus 1 be? If I play conservative, if it is a draw, what is sk plus 1 going to be? And if it is a loss, what is sk plus 1 going to be? And if you play aggressive, sk plus 1 equal to, if it is a draw, and if it is a win, what is it going to be? Tell me. Sk is already given to be sk, small sk. If you are having problems with it, you can write s as well. is given, the value of the SK is given to be S. Tell me.
S plus half.
Half. What is S? S is points of opponent A minus points of opponent B, right? That is clear. So if there is a draw, what will happen? A will get
Oh, same only. Same which would have been same.
B plus half, A plus half. So it's going to be still S or SK. And if it is a loss, it is a loss. So your points will remain the same, P, and this will be P plus 1. So you'll get to, yes or no? You'll get SK minus 1.
Yes.
Similarly, draw if you do again SK and SK plus 1. Fine. Not K plus 1 in the denominator, but addition. So now tell me what would be the value function going to be? So it will be the max of, so you play the conservative strategy. What if you play conservative? Conservative. What is the expected value going to be? So this is 0 given to me. So what is the expected value going to be? Versus if I play attacking or aggressive, what is my going to be? What is the value I'm going to get? Not difficult at all. So what is the probability of winning again? What are the two outcomes possible if you play conservative? It's the expected value of the two outcomes, right? So this is with probability PD 1 minus PD. This is with probability PW 1 minus PW.
So one thing, why did you consider only loss? We have won also. We have played conservative.
In conservative, there is no win. You never win.
Okay.
You only draw at the best case. You are playing for a draw. You either lose or draw. Fine. And if you play aggressive, you either win or lose. Is it clear?
Yes.
So now tell me the expected value then. The
PD
expected
to
value.
SK.
PD into SK or V of SK? PD draw.
Oh yes, V of SK.
V of SK plus 1 minus PD into V of SK minus 1. Yes or no? Right? This is just the expected value of VK plus 1, SK plus 1 given SK. That's what I'm writing. And there are only two outputs possible. If I play conservative, I'm writing on the left. If I play or a winning strategy, I will get P of win into, tell me, VK plus 1, SK plus 1, and plus 1 minus PW, VK plus 1, SK minus 1. Yes or no? Because you already told me I wrote the same equation. No problem. So you choose to play aggressive if what? Tell me. PW VK plus 1 SK plus 1 plus 1 minus PW VK plus 1 SK minus 1 is greater than PD VK plus 1 SK and 1 minus PD VK plus 1 SK minus 1. Is this clear? Questions? If the aggressive strategy is giving you more value function, more value, you choose it, right? Yes or no?
Yes.
So
So that's what
one
I'm.
thing, why did you do SK minus 1 for aggressive one? PK 1 minus PW, PK plus 1, SK plus 1 was there.
There are both. No, if you play aggressive, you can either win or lose. So Lose, no, acha, there's no draw. Sorry. I wrote it right correctly in the equation. It is right. 1 minus PW, and this is PW. Right? This is what you're saying.
Yes, yes, yes.
Yeah, that's a mistake. There's no probability of draw. So now, what will I get? I'll get PD into Vk plus 1 Sk minus Vk plus 1 Sk minus 1 plus Vk plus 1 Sk minus 1 Pw Vk plus 1 Sk plus 1 minus Vk plus 1 Sk minus 1 plus Vk plus 1 Sk minus 1. This and this cancels. So I get if PD by Pw is greater than equal to Vk plus 1 Sk plus 1 minus Vk plus 1 Sk minus 1 by Vk plus 1 Sk minus Vk plus 1 Sk minus 1. Then you play aggressive. So I'll do one special case and then I'll give 3-4 versions of the special case as homework to you. Say Sn I already know. The reward at Sn is known. I am going to do the value function at n minus 1 for Sn. Can anyone help me how to do this? For n minus 1. How many cases can I form and what? So this is the last game. So do you agree? So you have played 1 game, 2 game, and you have in the n minus 1th game, last game. And you're trying to decide the strategy for the last game. Fine. Now tell me what would be your strategy? Give me some cases which you will be considering. Do you agree? If S n minus 1, case 1, which I'm not going to even show, is greater than 1, you will win. You have won. Yes or no? If at the last game, previous to the last game, your points are more than 1, you can at worst lose. Yes or no? And if you lose also, it will still be 1. The 2 minus 1 at most can be 1. Right? It's again Sn minus 1 is defined as the points of player minus points of opponent. And if this is greater than 1, it means that player has already 1 game more, at least 2 games more. So already 1. So in a game of 15, he's already say leading 8-6. If the person is leading 8-6, he or she has won, right? Doesn't matter. Similarly, case 2, if Sn minus 1 is less than minus 1, already lost. So you can play any strategy for these two. Any strategy. Any strategy. Okay, fine. So now I ask you, if Sn minus 1 is equal to 1, what will you do? Help me with this. So V n minus 1 of 1 will be max of P draw into V n. Again, write it down from the top equation. Do you want me to copy it? Am I audible?
Yes, yes.
This is just one thing I'll just show, then we'll stop. Yeah. Okay. So now Vn of, tell me, Sk again. So it's like 1 that you draw, right? Plus 1 minus Pd into Vn of 0. Yes or no? Fine.
Yes.
Pw Vn of 2 and plus 1 minus Pw Vn of 0. Fine. Now put the values. What is Vn of 1? What is Vn of 1? After n steps, if you are positive, it means you get a reward of 1. Yes or no? That's what we define. So again, if you don't remember, Vn of Sn is just Rn, right? R of Sn. So what is the reward at if you are 1 after n games? We have defined it is 1. So this is 1. So I get max of PD plus what is the reward again if we are at 0 after n games? We defined this. This was probability of win. Right? That's what you're saying?
Yes, PW, yes.
Similarly, this becomes PW into what is the value of if you are at 2 after 1, that is again 1 plus 1 minus PW into PD or again PW. Correct?
Yes.
This is max of PD plus PW minus PW, comma PW plus or 2PW minus PW squared. So now let us see PD plus PW minus PD and 2PW minus PW square. Question mark I'm putting play aggressive. Right? I don't know which is greater, so I'm trying to find that out. No problem. I remove one of the P's from here. PD I'll take common 1 minus PW. I'll take common here PW 1 minus PW is greater than 1 again. PW PD. So this is not true. Not true. So because we have assumed PD to be greater than PW. So therefore play which strategy? The conservative strategy.
Conservative.
Good. So now your homework would be find PVN of case 3 would be case 3 and 4 will be your homework. Case 3 Vn minus 1 when Sn minus 1 is equal to minus 1 and case 4 where Vn minus 1 Sn minus 1 is equal to 0. Just do this. This entire dynamic programming will be clear. And if you have time, write the code and upload. To complete till 0. So I am already giving you all the code that I am doing. So I hope that you also try and do data that we have. So, okay, we are just on time. We have completed dynamic programming and other algorithms implementation like policy and value iterations and Q learning. So next day, what I'll do is it's going to be the last of the tabular methods and model-based methods, where I'll be doing stochastic shortest path problems, and I'll give you a flavor of how operators in linear operators in reinforcement learning work. So we're not going to go into a lot of control theory where you can prove a lot of convergences of these algorithms by using operators, but I'll do give you one flavor of a proof next day. So that's the plan for the next day, and then we'll see based on exams of students whether we'll continue for we take a break for a month or we continue with our classes. That we can decide after that. So I'm just stopping recording in case you don't have any questions regarding the not the logistics but the questions of the what we discussed. Any questions do you have? Okay, no questions. Thank you. I'll stop recording. Okay. So any questions?